Alright, continuing on with the bring up of these PCBs that I've created in KiCad, I have these boards are actually manually soldered, so there is quite a few problems with little shorts here and there, certain components not being mounted precisely right. So a lot of this debugging is about kind of figuring out where the shorts are and removing them, and one by one getting every single peripheral on this board working. So in the last two videos I've been taking care of the power. So I've been I've enabled regulators on two other boards where I have 12 volts, 5 volts, and 3.3 volts, two regulators that are 3.3 volts. And this is the this is the second board. So what we are going to be trying to achieve with the third board is pretty much getting a LED to blink. So if we have a LED blinking here on the third board, it means that our power is working and our CPU is flashable. So that's the goal that I want to achieve with the third board. So I'm going to disconnect this board and I'm going to move it aside, and I'm going to take the third board, which is here. Let's see, is this the third board? Yes, this is the third board. So doing the same series of steps as I did for the other two boards, and just getting the power to work. And we're going to have to remove a lot of little shorts along the way, because I can already see some shorts here where solder paste got between the pins. So there are certain places where things are not really as they should be. So I'm going to start my heat gun, and I'm going to warm up the board a little bit here. And then I'm going to take my wick and I'm going to wick off all of the excess solder. Put a little bit of flux on it like this. And I'm just heating it up so it's easier to melt the solder, because there's a lot of heat sinking on this part of the board, because this is the power stage that is going to drive the motors. So it's designed to lead off the heat. So when I try to wick the pins of this chip, it doesn't really work very well. The solder solidifies really quickly. So preheating it is a good idea. And I'm gonna just remove some of the excess solder here. When working with a wick, I think it's a good idea not to drag the wick over the pins, because it's way too easy to bend some pins that way. So I just press with the soldering iron on the pins, and then I remove the wick. Oh, this is too much smoke. I'm gonna suck the smoke out. Hello. I don't know if you can hear me, because I have the fume extraction going here, so you're gonna have to put up with the sound for a while. Okay, so this one seems alright. It's a little bit more there. So let's see, just a little bit more. Oh, that's awesome. That means that my filters are working. I have a fairly complex command line for FFmpeg to get the streaming running, and one of the steps in that command line is filtering and compression. So I should be filtering out a lot of noise. So I was trying to filter out my fan that's on my laptop, and I think it worked fairly well compared to how it was before. Right. So I'm gonna check if I need to do anything else to get the 12 volts running. So I'm gonna just check for shorts on the 12 volt level. So I put my multimeter into diode mode, and I'm gonna check the. Actually, I need to solder the resistor, but I'll check that first. Yeah, that's good. So I need one resistor here. I'm gonna try not to forget the resistors this time. So in the last video, or in the video before last video, I forgot one of the resistors, and I was wondering why I didn't have 12 volts on the connector. So that was because I didn't have any connection there. Did it just fall off? Where is it? Where did it go? It just fell, and I can't see it. Where is it? Oh, there it is. Okay. So this resistor will connect the main power to the 12 volt regulator. And then we should double check that we have 12 volts, and then we move from there. Come on. It's cooling down too fast. So I use my hot air heat gun to heat up the board around it. Come on. There we go. Yes, I've upgraded to KiCad 5.1. Everything around the resistor is molten, but the resistor is only now melting. The solder on the resistor is melting only now. Okay, so that should be it. And next I'm gonna check for shorts on the 12 volts. So I shouldn't have any shorts from that fuse there to ground, which I don't. Which means I should have 12 volts if I power this on now. I'm gonna have to order some correct connectors, but this will do for now. Yes, they're getting so hot there. Poor little elements. Okay, so I'm gonna power this on. And I'm gonna check for 12 volts here, which I don't have. Nope, no 12 volts. So this must mean that we have a VMOT short, and that's a common problem when soldering this manually, I've found. So let's see if we can, yeah, we check VMOT there. And do we have a short on VMOT? Nope. So it's something else. What can it be? We don't have a short there, no. So it could be something around this regulator. Actually, I'm going to check the schematic or the PCB to see if there's anything else that's likely to be shorted. So let's see. So we are looking for 12 volts on this rail here, and it's really not that much around this chip that can be shorted. So it's probably something around here. Maybe some capacitors or some resistors are shorted or something else. Let's see if we have a V in. So if we have V in, and it's at the same level as my power supply, that means that the short is somewhere else. If we don't have V in, then it's something shorted on V in. Yeah, it seems to be shorted on V in. But where is it shorted? So C15, let's check C15. We have, right, C15 is this one. So we can check R39 on, actually, no, that's not shorted. But what can be shorted? So it could be a short. It could be something as simple as a short around the MOSFETs on one of the resistors here. So I had a similar problem on a different board where this was causing high current usage. But I can't see any apparent short. So it's something that gets shorted when the power is applied. I'm going to just fix anything that I can see. Anything I see that doesn't look normal. resistor is getting stuck on my tweezers. I need to clean my tweezers. And I need a bit more flux. When things start getting stuck, flux solves the issue. Awesome. So these resistors seem to be aligned. I'm going to align all the others here. Cool. And a bit more flux on this resistor here. And I also reheat the resistors around the regulator, just in case there's something that's being shorted or something. Oh, that's a lot of solder. I have to work it off. There is a capacitor with a lot of solder on it. Better. Well, they seem to be holding up. I know that all of the heating probably is destroying the electrolytic caps. But then again, this is a prototype. The boards that are going to be manufactured by PCBWay are going to be professionally manufactured, and then I wouldn't have to do all this crap trying to solve all the little issues. But this is still faster than getting the prototypes from any assembly house. This is just 10 days and a little bit more like spent on this kind of prep. I wonder though if I'm gonna get the PCBWay prototypes by the time probably like at the same time when I'm done with all of this. In which case it's a waste of time, of course. But we'll see. Okay, that's done. Move this over out of the way. Awesome. So, anything else here? What else could it be? We can check how much the electrolytic capsule weighs. Probably says in the data sheet. Let's see if there's anything about that in the data sheet. Doesn't say anything about the temperature. That's operating temperature. Up to 85 degrees. How much can they take though when being soldered? Okay, whatever. I've never had a part being destroyed when soldering at 250 degrees. If I go higher than that, then some parts melt, but not really, not that I got any part completely destroyed that it didn't work afterwards. It's possible that parts get like bigger error in their rated value if they're exposed to temperatures over a longer period of time, to high temperatures. But what I think happened though, like one of the things that I think did destroy my CPU on one of the other boards is that I used one of these. It's a pressured container with EPA clean. So it's like you spray it on the board to remove flux. But I think that the board was a little bit warm when I did that, and this high going from a hot temperature to really cold temperature, I think destroyed the CPU. I can't really think of anything else. I think it was something like that. But I'm going to debug that board later. At first it worked, but then when I did that, when I sprayed it with the cleaner after heating it up a little bit, then the CPU didn't work anymore. Okay, so yeah, I'm just gonna power it on and see if I get any. Yeah, I'm still getting high current. Why am I still getting high current? So I got it on like 0.7 volts, and I'm getting 2.1 amps of current. Where is all the current being led? Where does the current flow? Could there be something about PMOS? Could there be something about these resistors? If there is a short of some sort. I'm gonna fix them, even though it may not be this issue, but they're still a little bit off, so I'm gonna fix them. Make sure they're straight and not touching. The good news so far is that everything seems to work once all the shorts are removed that are caused by soldering. Well, not everything seems to work, but at least the basic flashing of the CPU, being able to send signals out of the CPU, that seems to work. So next step would be to validate the motor drives and the most important peripherals. But so far I haven't had any major issues with this board. Maybe that's gonna come, but I hope not. I hope this board will work exactly as planned. Then I'll be happy. I'm going to place that resistor so it doesn't touch the resistor beside it. So I'm working on this resistor here. This is part of this brake resistor circuit, and I think there was a short there, although I can't tell for sure. But I'm gonna make sure that there is no short if there was one. That's fine. C30. Could C30 there, sure. Although I should be getting some. Ta-da. Okay. That should work better. I think my... Okay, I'm gonna test this again, because I think my cable got slightly out of the multimeter. Let's see. Let's see if we get any. Right, so we have a VMOD shot. We do have a VMOD shot, but where is it? Oh, I think it's there. Actually, I think I see a slight solder bridge there. I'm gonna see if I can move it just with the solder in there like this. Maybe that's it. Let's see. Maybe that's it. Could this be it? Okay. Right, so not quite yet. Not yet. There is more, slightly more problems with the short on the 12 volts, but slowly I'm getting there, because now I don't have 2.5 amps when I have 0.7 volts. Now the current increases when I increase the voltage past 4 volts. So it could be something. Let's see. Actually, this one needs to be lit as well. Okay. What else could it be? Let's see. It's quite low. I should be getting somewhere around 300 or more. So that tells me that there is some short, not a full short, but like a half short or some short over a resistor or something. Or a short on the output. How about that? So the output is shorted. The output of the regulator is shorted. So there is something here. It could be one of these components. So let's see if we can figure out which one it is. C138. No, C168 and 38. That's 68 to get. C18 is not here. C30. Maybe C30. Could be. So C18 is supposed to be connected to ground, right? Yes. C155. Could it be R49? Could it be that resistor? An R48 maybe. We're really unlucky. Okay. there. Yep. The short is still there. Maybe the microscope can tell us. Let's see if the microscope can tell us. I can actually remove this microscope. It's a really cheap microscope. But it works. It's amazing. So can we see any short here? Like this. I really have to repeat the resistors again. There isn't really much to go after here. It can only be somewhere here. So the short is kind of, I measure it here. So it's from here to ground. So there can only be just one of these components or the chip itself. What is the composition of the lead-free solder you're using? Ooh, I found the short. So there is a resistor that had a lot of solder underneath it. So I have to leak it off. No. So this is the solder that I have. It says super solder wire. Doesn't say much more than that. It's probably leaded. I know that the solder paste is leaded. So the resistor I was looking at was R37. No, still short. Still shorted. Maybe it's underneath the capacitor. Maybe it's one of these. So this capacitor, this could be that the solder paste is shorting the pins underneath the capacitor. So I'm going to remove it and see. I think that the keycap default footprints for 402 components and even other components as well could use more spacing between the pads. Seems fine. What else is connected to ground? Actually, I should check. C168. Could it be C168? So I'm looking for any components that have pads that could be shorted. So anything that connects to ground from the output of the regulator. Yeah, I think it was this one. There's definitely too much solder there. Could be this one, it could be something else. We'll see. Let's see if we still have the short. We don't have the short. So it was that capacitor. So the solder got underneath the capacitor. It's a small capacitor. So I'll just show which capacitor it is. So the capacitor is over there. It's C168, and it's a small capacitor that had a little bit too much solder on the pads. Let's see. So I removed the capacitor now, and I don't have a short anymore. So the pads there need to be cleaned up so that they don't have too much solder. And then I think we should have 12 volts. And I'm also going to remove the Zeners because I found that they conduct enough to make the regulators a little bit hot. So they shouldn't be there now. I'm going to have to revise that part of the schematic. Okay. Let's see if we can get some 12 volts. And the moment of truth. Can we get 12 volts? And we have 11.75 volts. Awesome. So next I'm going to connect the next resistor. And first of all, I'm going to check if there are any shorts on the 5 volt regulator. And I think the safest bet is probably to remove that chip and wick the solder underneath it. Because it's such a tiny chip, and I'm pretty sure that there is too much solder underneath it. How do you mean using multiple rails of same voltage? Are the rails connected, or do you mean using multiple regulators? I think it gets expensive. I think what I would do, and the same thing for this design as well, I do have two 3.3 volt regulators, but what I'll do in Rev B is measure the current that is drawn from these regulators. So because I have the current sense resistors on every single regulator here, I can measure how much current is being drawn by each regulator, or from each regulator. And then I'll design the regulators so that they can provide enough current. I would split the power rail such that, just like I did here, but have it kind of like in a star topology, so that you have the regulator at the center, and then you have power rails going from it in different directions to different components. And I think it also depends. It also depends on how much noise you're generating. So, for example, if you have one portion of the circuit where you have a lot of switching going on, so you get a lot of noise on that rail, so that regulator has to work extra hard to maintain constant voltage. And then suppose you have a different portion of the circuit that is an analog portion that doesn't, where it's actually important to keep the noise out. In that case, I think it would make sense to use two different regulators so that you can have a stable supply for that analog portion. But that's only if there is a huge difference in, like if there is a high current load on one portion of the circuit, and then connecting an analog circuit to the same supply would very likely pick up on that noise from this high current load that is being switched on that supply. So that's what I did here with the reference supply. I have a separate regulator for the voltage reference, which is only connected to the VDD-A, and then I have another regulator that provides the main power supply for the chips, the 3.3 volts. It's not so much power usage. It's switching. So if you have, for example, on this board, there is low frequency. Well, it's a rather low frequency. It's 30 kilohertz, so I count that as low frequency. There is low frequency, high power switching. So that noise is gonna be ending up in different portions of this board. No matter how much shielding I put on the board, no matter how I design it, there's still gonna be always a little bit of that noise going into different portions of the board. And it's that noise that you have to think about. Could it be that noise can create problems in your circuit? And if it's digital signals, it doesn't have to be a problem. If it's analog signals, then you can have a problem, because then you can have, if you sample a signal and suddenly you have a load that lowers the reference voltage, so the voltage, the signal that you're sensing is actually much lower than it should be. So you get an error there, and you have no way of knowing how much error you have if your switching is unpredictable. But if it's a digital circuit, then it probably wouldn't even care, as long as the noise doesn't go past the threshold of the CMOS switching. So if you have like if you have a value that is supposed to be 0, and the noise is capable of pushing that value to a 1, then it's a problem. But if you can keep it sufficiently low in amplitude and make sure that it's bypassed properly around each circuit, then I don't think it could be as much of a problem as with an analog circuit. But I think you need to read up on it, and you need to analyze the specific circuit that you're designing, and try to think of what could be the implications of the variation in the voltage level on the power rail. Could it be a problem, or maybe it's not a problem? And if you're concerned about a load drawing too much current, then just use a converter that has overcurrent protection. For example, TPS 54360 that I use here, it has overcurrent protection, so it doesn't mind being shorted, for example. I can try that a bit later. It just kills the output voltage, so it lowers the output voltage until the current is within limits, which is very nice. I really like regulators that you can just short and nothing happens. At least nothing destructive happens. Obviously the voltage on the power rail will go down, but nothing gets burned up. Okay, so I need to wick that. I'm gonna wick the pads of that circuit. There was too much, let's see, yeah, there was too much solder there. I definitely see several blobs which need to be removed before we solder this chip back on. And this should give us 5 volts once this regulator doesn't have any shorts. is a super tiny chip. Like, have a look. Damn it, where is it? There it is. Almost lost it. So, I'm gonna show it in the microscope. So the chip is like, the chip is over here, laying on this inductor. This is what this chip looks like. It's a tiny package. Quite a weird package. But that's what it looks like. So it's gonna go over there. And I think it's just enough solder for the chip to solder on, but without it shorting. Let's double check. Double check this one. Yeah, these pads are connected, so they're supposed to be like that. Now, which way am I supposed to put this chip? I'm gonna check on one of the other boards because I can't see any marking on it after I've put the flux on it. But hopefully I can see some small detail that will just tell me which way the text is. I'm just going to check like this. So, is this the same way? I can see 67 there. Correct. I think it looks correct. T1. Don't see any T1 there. Yeah, that's a D. Okay. Yeah, that looks correct. So this is how I'm gonna place it. Look. And it's time to solder it. Put more flux in it so it glides around. Put some lube in it and solder it on. There we go. Should land into place, but there is something underneath it. What is going on? Could this be it? Could we get 5 volts now? I'm going to place another current sense resistor so that I get the 12 volts connected to the 5 volt regulator. LCC plus LGA package. I almost have to check. I'm gonna check once I have 5 volts there. I'm really curious about that package now. Let's see. So I'm gonna check if this is shorted in any way. So this should be here. Should be getting 5 volts on this rail. It doesn't seem to be shorted, so we're gonna see if we get 5 volts. It's the moment of truth. We have 8 volts. Oops. That's not correct. I think it has something to do with one of the resistors not being connected or shorted. Let's see. This one has feedback there. And one of these resistors can be shorted, which would explain why we are getting higher voltage. Oh yeah, there is definitely too much solder there. I need to wick the resistors. I think the lower resistor was shorted. Okay. What if I need to do anything else? Maybe it works. Let's see. If it doesn't work, then I heat it up again. Okay. And check. Do we have 5 volts? And we have 5 volts! 5.16 volts. Awesome. So, next step is to enable the 3.3 volt regulators, and after that, once I have CPU power, I will flash the CPU with a simple firmware that will blink this LED here. And then we're done for this video. But I'm gonna check this GPS GSM module, because I'm interested in GPS GSM modules. I ordered a module that I was gonna test from China, and I never got it. Oh, that's fun. Hardware user manual. It gets even more fun if the footprint is wrong. Sometimes there are errors in data sheets. So where are the measurements? Where are the dimensions of this footprint? There. So this is not a footprint. This is a footprint. Okay. So why is this useless? This seems to give you all the details about the footprint. Recommended PCB layout. Anyway, I'm going to move on with 3.3 volts while YouTube is encoding the video and broadcasting it to everyone, because it takes something like 20 seconds for everyone to receive what is happening here. So I will connect. First of all, I'll check if the 3.3 volts is not shorted. And 3.3 volts is, so the CPU power is not shorted. No, they seem to be fine. For once, there is no short. So next step is to solder the two resistors. You could have used Python to generate the footprint. Let me show you something. So I have a few scripts here. There is a package called KiCad Library Utils. And with this package you can generate footprints with Python. So you can program all of the spacings and then you just generate the footprints. It's really simple, very nice. Very useful for footprints that have a lot of repeated components. So for example, there is, let's see, schematic library, PCB. I wonder if it was here. I think it's probably in a different package actually. No, sorry, it's not KiCad Library Utils. It's the other one. It's the KiCad Footprints code. Let's see, KiCad Footprint Generator. That's better. So I've been experimenting with this thing, with this Python code, and generating some footprints that are more resemblant of the IPC footprints. So kind of like more similar to the footprints that Altium would generate. But I think the general idea is very interesting. So you just code your Python script like this. You have, for example, width, depth, and then you just do the math in Python and generate all the paths. So you just do KiCad mod append, and you can append a circle, you can append a pad, you can append all the different components. And you can even generate a 3D model using Python and FreeCAD, which is also nice. You can get a small simple box generated from a Python script like this. So it's definitely something to look at. Very useful for repeated footprints. Oh, I actually have to go now, so I have to leave in 2 minutes. Let's see if I can quickly... Or maybe this will have to wait. Maybe this will have to wait until next video. So I'll just leave the resistors laying on the PCB there, and I'll stop this video and I'll come back to this and do the flashing in the next video.